Okay, we will finish our discussion of Giancloi here. The rest of introduction, measurement, and estimating by talking about section 7 and 8. The first of these is order of magnitude rapid estimating. So a quick way we want to calculate, right, is we want to round to 1 sig fig and then calculate the value. Now your result should be at least to the right order of magnitude, and you want to round it off to the nearest power of 10. And though it's not actually exact answers, it helps you understand what your answer should be like, so that when you do all the math, if you can tell if your answer is going to be close or not. But again, rounding to 1 sig fig and doing that is easy to do. Diagrams are very useful. In fact, we're going to talk about this problem right here that you see in a second. But order of magnitude. So here's the first problem.
Okay, so we're looking at the volume of a lake. We want to estimate how much water is in a roughly circular, about 1 kilometer across, and you guess it, has the average depth of about 10 meters. So we're going to try to estimate the volume. A couple different ways to do this. I'm going to go ahead and say the volume of a cylinder, which is essentially what our lake is pi r squared over h, with h being our depth, right? So I'm going to look at the problem, and I'm going to say if it's 1 kilometer across, that it's half a kilometer for 500-meter radius, right? So our volume is going to be pi times 500 squared times our height, which is 10, and that's going to be all in meters. And then it's just going to be a matter of calculating. So my calculations are going to be pi times 500 squared times 10. And I get 7,853,982 meters cubed. With this information, obviously you want about 2, maybe 1 sig fig, we'll just say 8 million cubic meters. And that'll be our volume. The next problem we're going to look at is the thickness of a single sheet of paper. So what I would do is I would grab the textbook and I would count out sheets. Let's say, I'm going to say 250 sheets of paper, and then I'd measure them. And let's say I'd measure that to be 1.5 centimeters. If I want to know just the thickness of a single sheet of paper, essentially I would say this divided by 250 sheets should tell me in centimeters what the actual thickness of a single sheet would be. So we'll go 1.5 divided by 250, and I get 0.0006 centimeters. That's not it's not perfect, right? I mean, we could break it down a little bit more. We could use unit conversion. Let's say we move it 5 to the right, 1, 2, 3, 4, 5. That would be 600 micrometers, and that would probably be a number that at least you could talk about. I mean, if you could keep it at centimeters like this, but hard to visualize. But then you can use metric conversions to get there. So that is the thickness of a single sheet of paper.
Here's the second problem. And then here's the third problem.
Okay, so we're looking at the problem with we want to find the height of this building based on a couple of things. One, our height is 1.5 meters. Our friend's height with their arms outstretched is 3 meters, and we're looking right over the top of them. Your friend and you are approximately 2 meters apart, but the big thing is that you have to find this distance, right? And you can pace that off if you wanted to. So let's give it a number. Let's say from your friend to the wall 16 meters. So our total height, our length, is 18 meters. So we know this, and we know that we're trying to find this, okay? So the big thing is we want to use a quick ratio. We know that to block out this, to see the angle here, we have 1.5 meters, right, over 2 meters, which is our distance between us. We then want to know at what height, x, is it going to be 18 meters? And we just do a quick little cross multiply. So 2x equals, what, 27 meters divided by 2. X is about 13.5 meters. So we can assume that the height of this building is 13.5 meters given the information that we're providing. Again, estimate, not necessarily fact.
Dimensions and dimensional analysis. Dimensions are the basic units, and we write them as square brackets. So like if speed is distance over time, we use L, length, is distance, T for time, and then we L divided by T would be your dimensions of speed, right? Length, distance over time. If we want to add or subtract quantities, they must have the same dimensions. So for an equation to actually make sense, dimensions must be consistent. And that helps out. And so in addition, a quantity calculated as a solution should have the correct dimensions. So after you're finished, the dimension should be accurate. And we'll do some work with this a little bit just so we can see. But let's say, for example, we see this equation. And we do this problem. Perfect.
Okay, so here we have an equation. We just want to see if it makes sense to, with all the units, they cancel out properly to give us what we need. So V, velocity, we know velocity units is length over time. VO is initial velocity, that would be like a final velocity. So velocity units length over time. The 1/2 is really irrelevant, but I'll put it in there. Acceleration, as you've read, is length over time squared, and we're multiplying this by time squared. So we're multiplying this by t squared. Now, when we look at the algebra here, these cancel. So we're taking length over time plus 1/2 length. These units don't match. That means we can't add them together. That means our answer would not be in length over time units. It would be in length times, or length plus time over time units. So this equation, based on just doing a quick look at the units involved, isn't a good equation. Do things like this come up? Sure. Sometimes you think you have an equation, especially if you're doing a lab and you think your data matches. But to make your data match, all your units have to match up. So this is an example of something that doesn't match up in relation to what you just watched that shows something that does match up.